Okay.
Yep.
Okay, thank you very much to the organizers for putting this workshop together and also inviting me last year. So I'm going to talk about a generalized cohomology theory, which is an object of algebraic topology for quantum contextuality. So the idea is going to be to introduce this generalized cohomology theory within the next 25 minutes. And I'll try to give you an idea of how to use that object to detect contextuality. So the basic object that I'm going to talk about is linear constraint systems. So these are useful formulation of state-independent contextuality. So essentially, it's a very natural problem. So you have a linear equation over integer z mod d. So let's say you have a matrix equation mx is equal to b, where everything is over z mod d. So we are going to look for operator solutions, which are essentially unitary matrices of certain dimension. So I'll denote UM for matrices m by m, unitary matrices m by m. And these matrices are going to satisfy three properties. So the first one is the detorsion property, so which imitates the detorsion property of integer z mod d. And there's a certain commutativity condition, which I will explain in more detail. And there is the linear constraint, which comes into play as a multiplicative form of the linear equation. So this is going to be the main object of the talk, object of study of the talk. So today, as I said, a generalized cohomology theory is going to be constructed. And the classes in this generalized cohomology theory is going to correspond to operator solutions of linear constraint systems. Essentially, these collections of unitary matrices with these three properties. So how is the path going to go? So first, I'm going to tell you how to construct a space associated to contexts. And then I will tell you how to interpret operator solutions as maps into this space of context, but more correctly, a classifying space for contextuality. That's going to be a quotient space of the object in number one. So then there's a procedure that is very popular in algebraic topology called stabilization. And that procedure is the one that's going to give us the generalized cohomology that we are going to seek for. And of course, the first example to look at as a linear constraint system is Mermin square construction and the Mermin star construction. And these two constructions, they're going to turn out to give the same class. And that class, it's probably makes sense to call it the Mermin class in the generalized cohomology theory that will appear. And an interesting question to keep in mind, so the particular examples of linear constraint systems, they're actually binary constraint systems, like the Mermin square construction and the star construction. When the local dimension or d in z mod d is odd, then the interesting question is, are there linear constraint systems which admit an operator solution over unitary matrices um, where m is greater than or equal to 2, but not over u1. So these are going to be contextual linear constraint systems for the odd. So if you restrict your solutions to generalized Pauli group, then we know that no such thing exists. So one has to look at other observables outside the generalized Pauli group or Pauli group. Yeah. Okay, so what are the contexts in this talk? To be able to compatible with the setup, it makes sense to consider context as a collection of unitary matrices, which are detorsion, meaning that the d power of the operators are the identity, and they pairwise commute. So these are the first two conditions that also appear in the definition of a linear constraint system. But in a more compact way, in a compact form, we can think of these contexts as group homomorphisms from n copies of z mod d to the unitary group. And since the domain has these detorsion elements here, the operators in the image are going to be going to automatically satisfy condition 1. And also, since the domain group is also abelian, it's a commutative group, the target is going to consist of commuting operators. So 1 and 2 is automatically satisfied just by considering these, looking at context as group homomorphisms more concisely. So the hypergraph formulation of linear constraint systems is a very convenient way of thinking about them. So as I said, a linear constraint system comes from an equation mx is equal to b. So we can reformulate it using a hypergraph H and a function tau. So the hypergraph, the vertices of the hypergraph encodes the variables x from x1 to xn. The edges are going to correspond to non-zero rows in the matrix M. And the entries of the M, they are going to correspond to an incidence weight on the hypergraph. So this 1, 2, 3, they are parts of the hypergraph, and the tau is a function on the set of edges of the hypergraph to Z mod D, and it encodes the column, the part on the right-hand side. So you can either think of them a linear constraint system as a matrix equation like this, or just precisely in the same way, it's a hypergraph plus a function tau. So an operator solution, to be more precise, is a function on the set of vertices to unitary group, such that for each edge, the set of operators restricted to the edge is going to be a context. So they have the first two properties being detorsion and pairwise commuting. And the third is the linear constraint, which is precisely given by the matrix equation in the multiplicative form. So the weight, incidence weight appears as the powers of the operators. And on the right-hand side, we have the tau appearing as the power of omega. And omega here is the d to the unity. So this is the third part of the linear constraint system. So a linear constraint system is contextual if it admits an operator solution over UM for m greater than or equal to 2, but it does not admit an operator solution, also called a scalar solution over U1. So this is the definition. So it's precisely state-independent contextuality. And famous example of Mermin square and star examples are going to be these two as depicted here. The purple context, they have the function tau there is going to be 1, and otherwise the function tau is 0. So I'm not going to tell you why this is contextuality. Probably everyone knows how to derive the contradiction. So our goal today is to consider these operator solutions. They are given by as a 2-qubit solution on the left-hand side and a 3-qubit solution on the right-hand side. So these are Pauli matrices, essentially. So I'm going to tell you how to interpret these two classes as a class in the generalized cohomology theory. So the first step is to reinterpret these hypergraphs as a topological space. So I can define a topological realization for a hypergraph, so which is a connected two-dimensional cell complex, whose one cells are labeled by the vertices of the hypergraph, and the two cells are labeled by the edges of the hypergraph. And the attaching maps of this cell complex, it is going to encode the linear constraints, but up to a scalar. So this up to a scalar part is going to be defined more explicitly when I talk about the classifying space for contextuality. It is going to amount to taking a quotient with respect to the scalars. So here in the Mermin square and the star pictures, they turn into these two pictures. So both pictures essentially is a space, they represent a torus. So the top parts and the bottom parts and the left and right sides of these squares, they are identified because they are labeled by the same operator. And similarly for the right hand side. So these are two tori which have different cell decomposition. So the left one has triangulates as the unit cells, and the right hand side has rectangular shapes as the cells. And the tau function that appears in the definition of the linear constraint system, it is turned into a two-dimensional cohomology class. So essentially, it is a function on the cells, which takes 1 on this purple one and the 0 otherwise on the other cells. And similarly for the Mermin star construction. So these two are going to be for a topological realization. These two constructions are important to keep in mind. So what are the properties of this kind of approach? So first of all, as I said, the tau function is going to correspond to a 2 cocycle, so which is going to be a two-dimensional cohomology class on the topological realization. And essentially, the linear constraint system is scalar, has a scalar solution if and only if the cohomology class is 0. So that's the role of the cohomology here. It detects scalar solutions in this way. Digging further, one can show that an operator solution exists, but no scalar solution exists. If a operator solution exists, but no scalar solution exists, meaning that we have a contextual linear system, then any topological realization is supposed to have a non-trivial fundamental group. So this is already observed in the torus example. So we know the Mermin star and square linear constraint system, they are contextual, and we have these 2 non-contractible loops in the torus. And this is a general phenomena happens for solutions of linear constraint systems. In a way, this is generalizing Arkhipav's group-theoretic characterization of contextuality, which only applies to d is equal to 2 case and certain types of hypergraphs. So more precisely, we are actually generalizing only one direction, but that is one can go further by including homotopy into the picture. Okay, so far I've talked about the linear constraint system, but what about the operator solutions? How are we going to topologically realize them? The way I describe the operator solutions, they are placed on the edges of the topological realization. But there's a more precise way of thinking about this. So let me describe this next. So first goal is to be able to realize operator solutions as maps is to construct a space. So this space is going to be a cell complex again, and its n cells are going to consist of n tuples of context. So again, remember that the contexts are group homomorphisms from the abelian group. And the way we think about these cells are, they are essentially an edge for 1 dimensions, and triangles for 2 dimensions, and 3-dimensional tetrahedrons, and so on. So these are essentially simplices. It's more correctly called them simplices. There's a way to glue all of these separate pieces into one whole piece, and this whole piece is called this space for contextuality, for context, and I will denote it by BDM. So there are 2 parameters here, the unitary group and the D here in the integers mod D. So the simplest example of this is when the unitary group is 1. So we are looking at context in the scalar group essentially. So that gives the classical object, which is a classifying space of this group mu D. So this is the multiplicative group, which is generated by omega. So omega was the features of unity. So this space is also studied in algebraic topology. So there is a version of this which omits this D-torsion part, only looks at the pairwise commuting unitary matrices. So in this talk, I'm only going to consider a D-torsion part because it's more compatible with the linear constraint system that we are looking at. But essentially, as I said, the topological space, the topological realization looks at linear constraint system after scalars. So that means essentially we need to take a quotient of this classifying space, BDM, and obtain another space, which is B bar DM. And the identification is that we have an n cell, and we are identifying 2 n cells if the operators differ by a scalar in mu D. And in this way, there's a recipe to turn an operator solution into a map between the spaces. So here XH is an topological realization, and the target is this quotient space. So this map is defined up to homotopy. I'm not telling how it is defined, but in the Mermin square and the star examples, putting the observables on the edges essentially defines this map. So that is how it is done in the examples. So one can define an equivalence relation on the operator solutions once we have these 2 maps, because now we can introduce the relation of homotopy and say 2 solutions are equivalent if and only if there's the maps, corresponding maps are homotopic. So this is the way we are going to group operator solutions into classes and then study these classes. So in the case of the square and the star examples, again, so these are very useful because if you look at them together and upgrade the Mermin square solution to a 3-qubit solution by appending an identity from the right, we can think these two solutions as 3-qubit solutions, and then we can construct a homotopy between these two things, essentially between the maps between homotopy between the maps corresponding to these operator solutions. So here S1 cross S1 means the torus. It's a topological notation for that. So the homotopy amounts to finding a refined cell decomposition of the torus. And it can be done for these two cases. So square and the star operator solutions, they essentially fall into the same class under this equivalence relation of homotopy. Okay, so but in general, the problem is that if you want to study these maps directly, then it is very hard. So because essentially we don't really know this space, we don't really understand the space very well. Homotopy groups of this space is really hard to understand, so it's not known. But we will try to overcome this problem in a two-step procedure. So the idea is a stabilization. So which means essentially considering all the unitary matrices all at once. I can consider a unitary matrix M by M inside a unitary matrix M plus 1 by M plus 1 by including it via this map. So A goes to A001. So I'm just including a 1 on this right diagonal. And we can take the union of these unitary maps along these inclusion maps. So the U infinity is called the stable unitary group. On the space of levels, level of spaces, we can do the same thing. So we can just look at the induced map between these context spaces of contexts and then take the union of the spaces. So we get BD infinity at the end. So it looks like we are making things complicated, but at the end, actually, everything becomes much simpler, as we will see. So to study this space, we need to pass to projectors from observables. So this is an interesting point. So there are two ways of looking at contextuality. One of them looking at the projectors, and the other one is looking at the observables. The linear constraint system, they focus on observables, and that's how we constructed everything up to this point. And then after the stabilization process, to be able to understand the homotopy type of this point, it is naturally the way to proceed is to pass to projectors. And the reason we will see in the next slide. Okay, not this one. So what do I mean by passing to projectors? So a context specifies a projector measurement, which is essentially a function that sends an element of Z mod Dn to a projector, which projects onto the common eigenspace of these operators corresponding to the eigenvalues, omega to the power s. So this is a projector measurement. And then, since we are sending M to infinity, we can do the same thing for the projective measurements as well. So essentially, we are going to look at functions into projectors. And on the right-hand side, the notation means that we are looking at projectors which project onto finite dimensional subspaces. So C infinity is again something quite finite, although you see an infinity here. It is the union of CMs as M goes to infinity via this stabilization map again. What we achieve by this is going to be a complete description of BD infinity. So after stabilization, I'm passing to projectors and imposing the partial sum. So this is the second ingredient in the understanding of the space. So we have this partial monoidal structure on the set of projectors, namely when two things are orthogonal, we can take a sum. So this is not quite an abelian group, but even having this partial operation always simplifies the structure of topological spaces. So more formally, we have a gamma space. So the BD infinity space, after passing to projectors, we obtain a gamma space that is called K mu D. So for gamma space, just think of it as a collection with certain compatibility, which I'm not going to define. But the good thing is, once you have this extra structure of gamma spaces, you can construct a generalized cohomology theory out of it. So this is a classical theory. So the step one is done. We have understood the stabilization of classifying space of context. What about classifying space for contextuality? It's not as straightforward as this quotient map, because the stabilization doesn't really descend to this quotient. there's a way to do it in a slightly different way. So remember, the B bar space is a quotient of the space, so it's happening in the category of spaces. Now we have obtained K mu D, but we want to consider a quotient of this, which is going to correspond to the quotient B bar. But now on the right-hand side, quotient takes place in a different category. So you can think of the category of stable spaces or the category of generalized cohomology theory. So they're essentially the same thing. So I'm not going to go into details, but anyways, so there's a way of obtaining another generalized cohomology theory from K mu D, which can be used as a stabilization of the B bar space. So, okay, so what is nice about this cohomology theory is that when you have a connected two-dimensional cell complex, like a topological realization, just think of torus or a two-sphere, for example. So these are two-dimensional cell complexes. Then the CDM cohomology evaluated on this space essentially gives us two parts. So the first part is the first cohomology of the space in Z d, dm. And the second part is H2x ZDM. So ZDM here means that integers modulo the greatest common divisor of DNM. So you get the first cohomology and the second cohomology of the space in these coefficients. So essentially, we are computing something for any topological realization. So these are the labels for the operator solutions. So how does that work? So you start from a linear constraint system and an operator solution. We can construct this map from a topological realization to the B bar space, and then we can stabilize everything to obtain these two classes, phi1 and phi2. So they correspond to H1 and H2, elements in here, H1 and H2. So the nice thing about this thing, when you start from tau, the cohomology class of tau actually coincides with phi2. And that is how you connect the classes in this cohomology theory and scalar solutions, existence of scalar solutions. So natural result out of this theorem is that if DNM are coprime, then every linear constraint system that admits an operator solution over UM admits a scalar solution. So this is not the only proof of seeing this, but this just falls out naturally from the theorem, because if DNM are coprime, you have CDM equal to 0 and tau is equal to 0. Therefore, you have a scalar solution. So more interestingly, the Mermin square linear constraint system, once you tensor it from the right by identity matrices, we can see it as a unitary operator over the unitary matrix of 2n by 2n matrices. And the cohomology theory applied to the topological realization, which is the torus in that case, if you apply the theorem, you can compute it. It is going to be 2 copies of Z mod 2 and 1 copy of Z mod 2. Now you can ask, what is the Mermin square operator solution going to correspond in this group? What is the element that it corresponds to? So let's call the Mermin class Mn. That's the element in here. If you compute that, that requires a computation here, it turns out to correspond to the element 0, 0, 1. So essentially, the 1 here tells us that this is the second cohomology. This tells me that there's no scalar solution, essentially. The other parts being 0 is also interesting, because that means you can replace the torus with a 2-sphere, and you will still realize the Mermin class there. Okay, so to conclude my presentation, so going back to the question of odd local D, so we can do the case of interest is when M is equal to a power of D, right? So that means you have a tensor product, n-fold tensor product of C to the power of D. So you are looking at qubits, for example. In this case, if you look at this cohomology theory, you have the first cohomology of X and the second cohomology of X. So this greatest common divisor just becomes Z mod D. And then these classes, whenever they are non-zero, you can ask the question, are they actually coming from a linear constraint system? And this is an open question. So one can try to construct these things. And once you construct a linear constraint system with an operator solution, you can look at the image. Where does it actually go in this cohomology theory? So as you see, the Mermin square gives us a non-trivial, interesting class. So furthermore, generalized cohomology theories also classify SPT phases. So you can ask, actually, does this generalized cohomology theory also classify any SPT faces. If you look at the real case, meaning that if you replace everything in this construction, replace complex numbers with real numbers, you can construct a cohomology theory, which is the real version of CDM. In this case, applying this construction to the true sphere, there are two parts. So the one part is coming from the Mermin square operator solution, because the solution is over real matrices, so you can think of it again, just the same construction goes through. And the other part is coming from a fermionic SPT phase constructed by Bouvin. So this can be shown. So this is an interesting connection to SPT phases as well. Okay, well, thank you very much for your attention.
Thank you very much, Cihan. We have 5 minutes for questions.
Okay, perfect timing, man. I did.
So questions and comments regarding the talk by Cihan Okay?
I have a question here. Robert speaking.
Yes.
About the very last thing that you said, Cihan, about this connection with SPT. I mean, can you flesh it out? I mean, there is connections from SPT to measurement-based quantum computation, and there's connection from contextuality to measurement-based quantum computation. So maybe MBQC could be a middle ground. I mean, do you have what I want to ask you is, do you have a concrete aspect or a concrete example in mind where you see SPT aspects as the physicist would recognize them, and where you see aspects of contextuality?
Okay, yeah, thanks, Robert. Yeah, so that's a very good question, and something that's I've been thinking as well. But I think the connection to MBQC at this point requires some thought. So the way these classes appear, so the Mermin square part is quite explicit. So we have this construction of, well, essentially the Mermin squares construction. So you can go through the way that class comes about, so which is essentially following this sequence of lines here, starting from the linear constraint system. This is we know very well, and this part also we know very well, the topological realization of the Mermin square construction. And the last bit is kind of the mysterious part, and that requires more study. In the SPT phase case, this connection to this particular SPT phase is even more disconnected from the combinatorial part, which is, I mean, combinatorial, I mean the lattice models. Because the way I was able to see this class in here was to use homotopy theory. And in that case, people have already passed from lattice models to the corresponding classes in the generalized cohomology theory that they were looking at. So that means for SPT, there's a similar line of thought like this. So instead of starting from a linear constraint system, so this is the combinatorial thing that we are looking at, people start from lattice models, right? And then from there, there's a way to go to generalized classes in generalized cohomology theories. Of course, you don't use CDM, but you would use some versions of K theory or some versions of cobordism theories. And the way I looked at this class, I looked what their class corresponds to on the right-hand side and compared the generalized cohomology theories. So essentially, there are two things to look at in this diagram. One is to understand the precise relationship between the lattice model that corresponds to the Bouvin phase and the class in the CDM cohomology. And the other thing is how they are interacting inside this cohomology theory with the Mermin class. Yeah, so the links are kind of requires more thought and more detailed study of how these classes come into existence. And I think the computational role of these two things is also related in the MBQC part, except that I think in the MBQC we are looking at bosonic phases instead of fermionic base phases. So I'm not sure how to turn a fermionic. So this is a 1D fermionic phase, essentially, how to turn it into something useful for measurement-based quantum computation, because usually we look at bosonic ones. So that's the other thing to see connection. So that there are too many things, the SPT, linear constraint system, and also I should put the measurement-based quantum computing. I think this link is already, I'm not very familiar because this is fermionic. This link we know, also the interaction of these two inside here is also missing. So yeah, that's a very interesting direction to go. Yeah.
Thank you.
Okay.
Okay, thank you very much. In 10 seconds left, probably there will be no questions and answers. I would like to ask then everyone to thank all our speakers. I thank Cihan as our last speaker in this session. And we will move to the last phase of our